Hello, my name is Debosmita Bhaumik. I am from NYU Game Innovation Lab. Today I am going to present our work, Tree Search versus Optimization Approaches for Map Generation. My co-authors are Ahmed Khalifa, Michael Green, and Professor Julian Togelius. In this work, we are going to compare the performance of tree search algorithms with optimization algorithms for content generation problem. Some background about this work. Optimization algorithms are popular choice for procedural content generation or PCG. There are a lot of research work exists where optimization algorithms are used to search the game space for good game content. This is because it is easy to frame content generation problem as single point or population based optimization problem where the fitness can be cleanly mapped with game elements. On the other hand, tree search algorithms are commonly used to solve pathfinding problems and creating game-playing agent, such as Mario AI Benchmark, Go, chess, general video games, etc. Though tree search algorithms can be also used for content generation problem, there are very few examples exist where tree search is used for PCG. Some examples are UCT for PCG, Monte Carlo tree search to guide platformer level generation, Sokoban level generation with Monte Carlo tree search, generating Angry Birds level using Monte Carlo tree search, exhaustive and semi-exhaustive PCG, etc. So, tree search is not widely used for content generation problem, and in most of the works where tree search is used for PCG, Monte Carlo tree search is used. Other tree search algorithms are not explored much for content generation problem. So here we are interested to know why tree search is not widely used for content generation problem. Is tree search a bad choice for PCG or it is not explored much for content generation problem? We know that optimization algorithms perform well in PCG problem. We try to use the tree search algorithms and optimization algorithms for same content generation problem and compare their performances. We are interested to know if any of the tree search algorithm can perform similar or better than the optimization algorithm. If yes, then in which cases? For this work, we are going to use 2D level generation problem. We have selected 3 games from PCGRL framework. The first game is binary. Here, the goal is to generate a level which is fully connected and the length of the longest path is greater than a predefined value x. The next game is Zelda. For this game, the level should be fully connected, have one key, one door and one player. Distance between any enemy and player should be greater than a predefined value x. Distance between player and key and door should be greater than a predefined value y. Our last game is Sokoban. Here the levels should be connected, have one player, number of crates should be equal to number of goals and can be solved by an A-star algorithm in at least x steps. We have selected these games as they have different kind of heuristic functions and these games are previously used for several research work. To search the level space using tree search, the levels need to be represented in such a way so that it can be searched efficiently. We imagine every level as a node in the search space and any modification in that node leads to another node. For this, we are introducing 3 different representations. The first one is narrow representation. In this approach, one specific tile can be modified at a time. Here, the tiles that the algorithm can modify are randomly ordered and the level can be modified in that specific order only. If this is a root node and the order of these tiles are x1, y1, x2, y2 and so on, then at depth 1, the algorithm can modify the tile at x1, y1 only. And at the next depth, it can modify the tile at x2, y2 and so on. Next representation is wide representation. In this representation, the algorithm has more freedom compared to the narrow representation. Here, the algorithm can decide which tile to modify. Starting from this root node, the algorithm can choose any tile for modification. Our third representation is turtle representation. This is very similar to the turtle graphics module in logo programming. In this representation, the initial level is given a random starting position. It can change its current position by moving to any neighbor tile in 4 cardinal directions or modify the current tile by changing it to another tile. For comparison, we have selected 4 very commonly used tree search algorithms and 4 optimization algorithms. For tree search, we have selected 2 uninformed search algorithms. These are breadth first search and depth first search, and 2 informed search algorithms. These are greedy best first search and Monte Carlo tree search. For optimization algorithm, we have selected 2 single point optimization algorithms, hill climbing and simulated annealing, and 2 population based optimization algorithms, evolutionary strategy and genetic algorithm. In experiment, we run each tree search algorithm using each representation for each game. We run the optimization algorithms for each game using wide representation only, as it is the direct representation used for the optimization algorithms in previous research works. We run each experiment for 2500 runs, and all runs are restricted to 60 seconds. If the algorithm finds a solution in the given time, it returns the solution. Otherwise, keep searching till timeout. Now, let's look at the results. These graphs shows the percentage of playable levels found by algorithms for different problems using different representations. From this graph, we can see that breadth first search and depth first search performed very low in all problems using all different representation, while greedy best first search performed pretty well in first 2 problems, while it performed little low in the third problem Sokoban. We can see that greedy best first search using all representations performed similar to the optimization algorithms. In binary, Monte Carlo tree search using narrow and turtle representation gave nearly average performance, while it performed very low using the wide representation on the same problem. Also, in Zelda, MCTS performed very low using all representations. But surprisingly, in Sokoban, MCTS performed better. Using the narrow representation, MCTS outperformed all other algorithms. Here, it performed better than the optimization algorithms also. Now, let's look at these graphs. These graphs shows the depth reached by the algorithms in given 60-second time. Here, we can see that breadth first search cannot go very deep in the tree in given 60-second time, which explains why it performed very low in all the given problem, where depth first search goes very deep in the tree compared to breadth first search, but it still performs low, as depth first search has a tendency to trap itself in bad initial branches where it wasted most of the computation time and cannot explore the other branches. Greedy best first search goes average depth in the tree in all of the problems. We can see that MCTS never goes very deep in the tree due to the exploration and random rollouts. In the previous slide, we have seen that MCTS performed very low in binary using wide representation. Here we can see that for that problem, MCTS cannot go very deep in the tree. This is due to the high branching factor of wide representation. Similarly, in Zelda, MCTS creates a very shallow tree because the large map size and big number of possible tiles in Zelda makes the branching factor bigger in this problem, and MCTS wastes most of its computation time in low-level nodes, as it cannot go deeper until it explores all previous childs in that branch. In Sokoban, Monte Carlo tree search outperformed all other algorithms. Greedy best first search go deeper in the tree using narrow and turtle representation compared to MCTS, but still cannot beat MCTS. On the other hand, MCTS did not go very deep but performed better. This is due to the deceptive fitness function of Sokoban. In Sokoban, good fitness value do not always lead to a solution. As example, this is an empty Sokoban level. When a crate is added here, its fitness value increases. Then, when a goal is added here, its fitness value increases more as the number of crates and goals are equal now. Then, a player is added here and now its fitness value remains the same as this level is unsolvable now. Because of this kind of heuristics, greedy best first search might waste time searching in those branches which leads to unsolvable level, while the random rollout helps MCTS to avoid these type of branches and help it perform better. In conclusion, greedy best first search performs similar to optimization algorithms in all of the problems. Monte Carlo tree search performed better in presence of deceptive heuristics. Right tree search paired with right representation can be used for content generation problem. In future, we would like to extend this work using bigger map size and more complex problems. Also, we would like to compare new state-of-art algorithms for both tree search and optimization algorithms. Further, we would like to investigate population-based tree search algorithms, treating the domain as a graph and using multiple starting points. Thanks for watching.